these two numbers added together will always equal 14. So what's this number right here? 11. So if we're looking at the hydrogen ion concentration, then here's my number. It's 1 times 10 to the negative 3. That's all it is. Because pH is the negative log of the hydrogen ion concentration, that's it. As long as it's in the format of this 1 times 10 to the negative whatever, then I can put it like that. So look at this. I've got the POH of 2, so what's the pH? 12. Is it an acid or a base? It's a base. Lower numbers acid, higher numbers bases. So again, this side is the part that we're really familiar with, that we have the whole line, the pH thing and everything. This side, we can use it in our calculations, in our Ka and Kb, we can use these numbers, but really, for all practical purposes, this is not the one we use. For the regular person that's going to go out and buy stuff at Walmart, they don't use the POH scale, they use the pH scale. So then when I look at the hydrogen ion concentration, what would it be? 1 times 10 to the negative 12. That's it. If it's in the format of 1 times 10 to the negative whatever, then I can just, it's really easy to do these numbers. But look at the next one down here where it's 2.5 times 10 to the negative 3. In that case, we have to stick it in our calculator and take the negative log. So this is the hydrogen ion concentration. So we want the negative log of 2.5 second EE negative 3. And I got 2.6, yes? So 2.6. It's not negative 3, it's actually a little bit higher than that, right? Yeah, it'd be like this. If we could write it like that, it'd be 1 times 10 to the negative 2.3, right? And this number's more than this number, yes? And if you look at that, that makes sense, because if I had 1 times 10 to the negative 3, 2.5 times 10 to the negative 3 is more hydrogen ions, right? So the pH here is lower, closer to the being more acidic than it is if it had just been a 3. Yes? Yeah. All right. So if it's 2.6, 14 minus 2.6 is what? 11.4. Still, when you add these two together, they have to equal 14. Okay? Here, we've got a pH of 6. So what's my POH? And then what's my hydrogen ion concentration? Okay, now what would you do in this case? Yeah, we're not allowed to write it as 1 times 10 to the negative 3.21. Pop that in your calculator. 3.21 and hit enter. You get that? Yeah, we're not allowed to do that. Can we do that with the caret button? So do the easy one first. What's our POH going to be? What is it? I'm sorry? 10.79. And then when I pop this in, and I'm sorry, my brain's gone dead here for a second. I have to play with this a little bit. So it'd be 1 times 10 caret 3.21. Oh, it should be negative 3.1. I think there's an easier way to do this. Yeah, that's not right. So how do I get the negative log of that one? How do I get the negative log of that one? I should get this easily. Negative log second EE negative 3.21. Yeah, my brain's gone dead here. So hang on. There's a simple way of putting this in your calculator, and my brain's gone dead I'm sorry, what? Can you do the opposite? Yeah? Will that work on your calculator? There's some way you can type it in and it just automatically puts it in the format that you need, and I just, for the life of me, I can't remember how to do that. I'll have to go get my pre-AP stuff and just, because it's something really simple, and my brain's just gone now. Let's see. So it should be 1 times 10 caret negative 3.21. So I got, okay, so if I take it as 1, okay, so if I put this in my calculator as 1 times 10 caret 3.21, then I get 6.17 times 10 to the negative 4. Did you guys get that? I put in my calculator as 1 times 10 to the negative 3.21. Isn't that what it is? And I'm sure there's some simpler way, and I'll go look in my stuff after this class period. So I put it in my calculator because I know that that this would be 1 times 10 to the negative 3.21, right? Yes? Yeah. So I put it in my calculator and then hit enter, and it gave me 6.17 times 10 to the negative 4. That's the hydrogen ion concentration. Really? You did that? Did you guys get this? Yes, no? Yeah. So I think, I think that's just, I think there's an even simpler way to do that than this, but I think this is the way it works, because really, that's exactly what it is, 1 times 10 to the negative 3.21. No, but all I did is say, well, it's 1 times 10 to whatever, but it's 10 to the negative 3.21. So it wouldn't let me do that as an inverse log. Inverse log. Is that what you're saying? Do you guys have an inverse log button? Inverse, so second, yeah, no, the second log, negative 3.21. Glory, there it has it. That's it. So second log, inverse log, second log, and then put in the negative, whatever this number is. There it was. Sorry. So if I want to know this, that took me a long time to figure that out. I'm sorry about that. So if I want to do this second log, right? That's the inverse, what you were saying, divide by our inverse log, negative 3.21. Did you do that? Is that what you did? Yeah. Yeah. So it's second log, negative 3.21, and that gives us that 6.61 or 6.17 times 10 to the negative 4. Yeah? Sorry about that. My brain just blipped for a minute. Yes? Yes, no, you guys got that? Yeah? All right. Write that down. So see how I wrote that down? Second log of negative 3.21. So this, we know it's the negative log of something. So if you do second log, that's the inverse of that, and then plug in your negative number. You have to plug in the negative number, and then put your type in your pH. So because the pHs, it's really nice if the pH would be a nice pretty whole number, but in reality they're not going to be that way. We'll have our drop counters out, and they will give us really specific numbers on in the pH meters. They'll give us really specific numbers on that. So there's no need, you're going to get better numbers than just 1, 2, 3, 4, 5, and so on. Okay, down here in the bottom part, in the second part here, when you have the hydrogen ion concentration and the hydroxide ion concentration, they equal the water constant. So look at this right here. Hydrogen ion concentration times the hydroxide ion concentration will always equal 1 times 10 to the negative 14. So when you multiply these two numbers, they're going to equal 1 times 10 to the negative 14. If it's in the format of 1 times something like these guys are, then it's all about the exponents. So 1 times 10 to the negative 4 plus what is 14? 10. So 1 times 10 to the negative 10 times 1 times 10 to the negative 4 is, you add the exponent. That's all you're doing. You guys remember that from baby math, right? So you love it when it's in the format of 1 times 10 to the whatever, because it's so easy when you do that. So 8 plus what is 14? So 1 times 10 to the negative 6. Yeah? You have to do a little tiny bit more work when you get into the format where it's not 1 times 10 to something, but it's still, they're going to equal this. So 1 times 10 to the negative 14 is going to be, look at your formula, it's right here. I mean, they gave you this one here. Multiply the 2 hydroxide and the hydrogen ions together, and you're going to get 1 times 10 to the negative 14. So it's going to be 1 times 10 to the negative 14 divided by whatever number you have. Divided by whatever number, always. So 1 second EE negative 14 divided by 2 second EE negative 6. Oh, what happened? I hit a wrong button somewhere. Oh, I stuck a comma in there. So I got 5 times 10 to the negative 9. Yes? So when you have these two, they will always, when you multiply them together, they're going to equal 14. The reason, you could multiply these two together, like if I put 1 second EE negative 4 times 1 second EE negative 10, there's your 1 times 10 to the negative 14. It's just easier when it's in that 1 times 10 to whatever format. All you're really doing is adding the exponents together to get that. That's what happens when you multiply numbers with exponents. You add the exponents. Here you had to do a little bit more work. So do the rest of those and compare your numbers. Why my light's blinking? Okay, so here's the kicker with this. It's really simple. You don't have to memorize it because it's on your AP pages. It's right here. pH, how to calculate the pH, how to calculate the POH, how to find the if you have pH and POH, how to get the overall pH. You can just 14 minus the pH or 14 minus the POH and you get the other one. And then also it's giving you the water constant. So it's giving you these things right here. It's giving you these things that you can use. These are things that you learned in pre-AP. We do every single one of these in pre-AP. Every single one. So this is baby stuff. You don't have to memorize it. You have to know where to go so that you don't have to shove it in your brain and keep it. You have to know where to go to find the information. These two right here are your equilibrium expressions for the acid and the base. These up here at the top are the equilibrium expressions for concentration and for pressure when you're not dealing with acids and bases. And then these two down here are dealing with weak acids combined with strong bases or vice versa. So we haven't made it to these two yet, so I'm going to erase my little bracket there. We'll get to those a little bit later. 4 moles of KOH and enough water to make 2 liters of solution. Again, that's just simple molarity. It's a nice little practice for calculating molarity, and that's it. Okay, flip it over to page 16. Now 16, we can get a little bit more stuff going on in here. So now we have acid and base equilibria. So when we look at this one, it says, here's your equation, and notice they're giving you generic stuff. It's H with some anion, and you're going to put it in water, and it's going to form, that H is going to hook up with the hydrogen, with the water and form the hydronium ion, and then the poor little anion is going to be over here all by itself. Write the equilibrium expression for the reaction. Products over reactants. Everything is aqueous except the water here. Everything's aqueous, so it belongs in the equilibrium expression. So this is an acid, so we're going to put Ka. Products, so we have the concentration of the hydronium ion times the concentration of the anion. Whatever it is, that's just generic. Divided by, I'm not going to put water in there because it's a pure liquid, right? I'm going to put in HA concentration. And if you look at your green pages, there we have it right here. Now, they used hydrogen ion instead of the hydronium ion. If this person who wrote this paper hadn't included water, then that hydrogen ion, that acid over here, we would have put just the H ion there instead of that, yeah? So if they didn't include water, it splits into those ions, yes? If it does include water, it splits into the ions, but this hydrogen ion just hooks up with the water, and it forms that hydronium ion, yes? It's just a different, look, remember these two are pretty much interchangeable. If the acid is a strong acid and it almost entirely ionizes in water, will Ka be very large number or will it be very small? So if this completely ionizes in water, which means it's shifted to the right, is it a big K or a small K? If the products are favored, it's a big K, large K. So large K, why? Because the products are favored. Heavily, because it's a strong acid, almost everything, really, if it's a strong acid, it completely ionizes. Everything, we just write it split up completely and we just assume it goes to completion that way. So if it's a large K, if it's a strong acid, you're going to have a large K because it's right shifted. It's way over here to the products. Pretty much everything is pulled apart there. If the acid is very, very weak acid and it ionizes very little in water, will K be very large or very small? So if it's left shifted where it almost basically doesn't ionize at all, is it a big K or a small K? Small K, really small K. Why? Because the reactants are favored. Because the reactants are favored. The reaction proceeds to a very small amount. The ionization, if you say ionization because that's what they're talking about, it just proceeds to a really small degree. Okay, look at the other side over here. So this was for an acid. Now look at the other part that says it's for a base. So here we have, here's the base. We put it in water, and the water is actually going to act like the acid. If you write the water as HOH, you can see it more. The water's acting like an acid. Bases are acceptors, right? Bases acceptors. So the hydrogen is going to be donated, and the X over here, the anion, accepts it here. So in this case, again, the water's liquid, but this is how it works. So here's your base, your hydroxide ion, and here's your acid over here. Write the equilibrium expression. Products over reactants. So in this case, instead of Ka, we're going to have Kb because we're focused on it being a base. How do you know when to write Ka and when to write Kb? Well, look what you have. There's the hydroxide ion right here, Kb. Products over reactants. So I've got OH minus concentration times the HX concentration divided by, am I going to put water in there? No, it's a liquid. We don't put liquids or pure solids into the equilibrium expression, so we have on the bottom. And again, when I look here on my green pages, here it is right here. They used B instead of X, right? So somebody, let's see, where are we here? Hydroxide. Yeah, they left off a plus sign. Yeah, this should be, well, no, it doesn't. They just put them, they've got it messed up here, don't they? Oh, well, I'll leave it as it is there because that goes with what they've got here, but it's slightly different on here with the pluses and the minuses. I think it just depends on how they're showing it right here. Yeah, it just depends on how they're showing it, but this goes along with what we've got here. So if the base is a strong base and it almost entirely reacts in water, will Kb be very big or very small? So if the reaction goes to completion, is K going to be small or large? Large. Let me see that again because you guys are looking at me like you're not quite sure. If a base is a strong base means you put it in water, it's going to completely separate into ions. It's going to completely separate into that X and the OH stuff. It's going to completely separate into that. So if it's a strong base, K is large. because the products are favored, heavily favored. It's a strong base. That's what it means. So Ka kind of leads you into, is it going to be far right or far left? Now, there are some in-betweens that it can be, but when we say strong acid or strong base, that means it's way, way shifted way over to the right. Okay, so, and the next one should say if the base is a very, very weak base and it reacts with very little water, will Kb be a very large number or a very small number? So if we have a weak base, are we going to have a large K or small K? Small K. Why? Because that word weak tells you that it's not going to ionize very much, so the reactants are favored. Weak means that it doesn't ionize much, it doesn't separate out. Because it was a typo. So, because on this side we're talking about bases, and on the other side we're talking about acids. Yeah? So yeah, it was just a typo. If the base is a very, very weak base, should be weak base, and it reacts with very little water, will Kb, yeah. So this side is just talking about bases. So it's a small K. Weak means that it doesn't ionize much, or at all. So small K. So reactants are favored. So, and that goes for any of them. If you have a big K, it means it's gonna, when they reach equilibrium, it's gonna be way over here on the right-hand side, with the products. If you have a really, really small K, it means the reaction didn't much go. Equilibrium was reached way over here with the product, with the reactants over here, so hardly anything happened at all. So if we have extremes in the Ks, that's a good thing. It's easiest to do. There's a gray area when you get right around 1, like just right at 1 or a little bit under 1. That's where you have some gray areas because it's going to be right around in the middle. But in most cases, they have us deal with really small Ks or large Ks, so we don't have to have that gray area. Okay, flip to the next page. That's page 17. And calculate the pH of the solution at equilibrium or at the end of the reaction if the acid is a strong acid. Okay, calculate the pH of the solution at equilibrium or at the end of the reaction if the acid is strong. What they're telling you here is they're saying, hey, if it's a strong acid, think of the reaction as going to completion. Yeah? Typically, if it's a strong acid, it's going to do this. So in this case, it's not that there's a chemical reaction going on. They're just wanting you to try and find the pH of this. So find the pH of 0.1 molar H solution. Okay, look at this. Haven't we just been doing 1 times 10 to the negative whatever? Can you take this number and put it into that format? It would be 1 times 10 to the what? Negative 2, right? What's the pH? That's it. It is a strong, now the reason I say that's it is because this is a strong acid. Strong acids completely ionize in water. So how much of this 0.01 or 1 times 10 to the negative 2 hydrochloric acid solution is going to ionize? Every single stinking bit of it. That's why we can do this. If we didn't have a strong acid, we couldn't do this. Remember, Ks are all about the reactions that don't go to completion. It's all about the weak stuff, the stuff that doesn't dissolve completely. That's what we're talking about here. Same way on the base. They don't have a base here. The same way on this acid. Is this a strong acid? Number 2, is it a strong acid? HClO4. Does it have 2 or more oxygens than hydrogen? Yes, it's a strong acid. So what is the pH? What is the concentration? Well, it's 0.0003. Can we put that in the scientific notation? 3 times 10 to the negative 4. So we need the negative log. pH is the negative log. of that 3 times 10 to the negative 4. Pop it into your calculator. Wow, I keep hitting buttons. And so what's your pH? It should be close somewhere around 4, shouldn't it? Yeah? And it is close to that, 3.5 something. There's your pH. pH has no units of measurement. So when you look at this, when it's in the format of 1 times 10 to the negative whatever, all you have to do is look at the exponent. If it's different from that, I've got more, so it should be slightly more acidic, right? So instead of having a pH of 4, I'm going to have a pH of 3.5. The lower the number goes on the pH scale, the more acidic it is. Now, when I look at number 3, is that a strong acid? Okay, that means I'm going to have to do more crap to it. So when I have something that's not a strong acid, then I know I'm going to have to work harder at it. And that's, again, it's always the K's are all about, well, which ones are strong acids? That's nice, but we want to work with the ones that are weak. I just lost it. There it is. So we want to work with the ones that are weak in that sense. So in this case, since we've got a weak acid, let's write out our equation. So, and they've written, this is acetic acid, this is vinegar, but they've written it out in the typical format that you're going to see on the AP test. So write your acid down, and let's write a reaction on how it's going to separate. So we've got CH3Cu, and this is aqueous, and it's going to split. It's weak, so it's going to split into ions. I'm going to have CH3 COO with the negative plus the hydrogen ion, right? I'm not putting in the water because, really I don't include it in my equilibrium expression, so I'm not going to waste my time. Roma, are you on the planet? Okay, so there's my R. If I'm doing a weak acid, I know I'm going to do a rice table. So here's my R, I, C, E. Here's my rice table. For those of you who fear the rice table, cut it out. Several of you guys, okay, so a few of you guys didn't put one rice table on that test. The rice tables help you. If you made a crappy score and you didn't use a rice table, maybe you should get your head up out of your butt and use one. Okay, so we have the rice table. So, what's my initial concentration of the CH3COOH? 0.01. And my initial concentration of the other parts are 0 and 0, because they weren't separated at all at first, right? You just put it in there. They're going to change by some number, so this is going to change by some number x. This is going to increase, isn't it? So it's going to be plus x, and this one's going to increase by the exact same amount because it's a 1-to-1 mole ratio, right? Everything, when I balance this, it's all 1-to-1. Yeah? And then at equilibrium, that means this is going to be 0.01 minus x, and this is going to be x and x. So when I put this in here, I'm thinking, well, here's my equilibrium expression. So I've got Ka. What's my equilibrium expression? Ka equals what? Products over reactants, right? Products, concentration of the products divided by the concentration of the reactants. And if we had had water in there, this would have been H3. This would have been written as an H3O+, but the water wouldn't have been in here anywhere because it's a liquid, so we don't include it. Now, I need another piece of information because I'm going to have X's all over the place and then another X over here because I don't know what it is. Look down at the bottom of that paper. It tells us the K values for the weak acids. Look, right, that's what it is right there. So they've given us what K is equal to. So K is equal to 1.76 times 10 to the negative 5. So I've got that number to plug in there. So in most cases, they're going to have to give you what k is so you can calculate. They can't have you, well, calculate x and calculate k. You don't have the data for that. You have to have more numbers than that. They have to give you what you need. They can't just say it's, nothing. So what's the concentration then? Well, I just said it was x times this one's x divided by 0.01 minus x, right? Do we have a really big x, or do we have a really big or small k? Yeah, we have a pretty small k. What that means is if I subtract x from this number, it's like, it's still going to round to 0.01. Well, it's not going to be any difference at all. So because k is so small, ignore that minus x. And that means you don't have to use the quadratic. So what we have then is 1.76 times 10 to the negative fifth equals x squared divided by 0.01. Now, solve for x. So I'm going to multiply by 0.01 on both sides, right? And then take the square root of that. And I got, what did you guys get? I got 4.195 times 10 to the negative. Yeah, something happened there. I don't have negative 4. I did on here. Yeah, I hit the wrong button. So I got 4.195 times 10 to the negative 4. Okay, now, that's x. That's the concentration of the hydrogen ion, right? So this x equals the hydrogen ion concentration. Is that what they're asking us to find? What are they asking us to find? It says find the pH. If you have the hydrogen ion concentration, how do you find the pH? The negative log. So you've got to take one more step. The pH equals the negative log of this 4.195 times 10 to the negative 4. And I got 3.38. How many sig figs should we have? Look up here at how many sig figs are up here? 1. I hate that. So our pH is 3. Yeah, we don't use this number because this number just came off a chart. Yeah, so our pH would be 3. That's what you could put on there. Okay, see if you can do the one over here to the side. Find the pH of 0.01 molar HIO solution. Same exact process. Remember that your Ka, look down at the bottom of the page. So they gave us Ka for this, and you have to have that. Is Ka really small? Yes. Praise Jesus. So you can ignore where it says minus x here. Remember, you can ignore that, correct? Okay, what's your hydrogen ion concentration? What's X? Your molar solubility, or your hydrogen ion concentration, X, equals what? .47 times 10 to the negative 7. That's your hydrogen. That's the molarity. Again, they'll call it molar solubility if they're talking about things dissolving. They'll call it hydrogen concentration. It's in molarity. But you're not done there. If we were doing KEQ or KSP or KC or any of those, then we would be done here. But in this case with acid bases, we want one more step. They're going to ask you the pH. So this is your hydrogen ion concentration. Take the negative log of that. So your pH is the negative log of that 4.47 times 10 to the negative 7. Are you guys coming up with the same numbers? Yes? So what's your pH? 6 point something?
6.35, but then you round it to 6.
Yeah, and then it's got 1 sig fig, so the pH is 6. Which, again, I don't like that. Questions? Can you explain it to someone? Could you? Yeah? I gotta tell you, this is still a pre-AP paper. Okay, so how much time do we have left? Okay, so I want you guys to do something as homework. This will be your first grade of the next 6 weeks. You need to watch a video and fill it out. So, page 11. Page 11. That's you slackers online too. Page 11, acid base, it's crash course chemistry number 8. It'll take you a whopping 12 minutes max. So, you have homework. Yes.